Let's have a look at electric dipoles today.
Okay, so next thing I'd like to talk about is an electric dipole. So an electric dipole is basically when you take a positive and a negative charge. So here's what an electric dipole looks like. It's two equal and opposite charges, like a positive Q and a negative Q, separated by a distance d. That's how we model an electric dipole. Electric dipoles are kind of important because a lot of molecules behave like an electric dipole. An example of that would be a water molecule. It is polarized, right? One side is slightly positive and one side is slightly negative. So it's useful to be able to describe these sort of creations that are neutral, but the charge is separated a little bit, like this. So this dipole here, plus Q and minus Q, it is overall neutral, but it creates an electric field around it because there's a positive charge and a negative charge. So if I want to find that electric field at that blue dot there, there would be an electric field created by the positive charge. So the positive charge would create an electric field at this point pointing away from it, right? So this would be the electric field created by the positive charge. And that would be due to this distance here, right? We'll call it R plus. But there would also be electric field due to the negative charge. And I'm going to make it smaller, right? Because the negative charge is further away. And the electric field due to the negative charge is going to be this distance here, R minus. So the electric field created by the positive charge is going to be stronger because it's slightly closer to that point. And the electric field created due to the negative charge is going to be slightly weaker because it's slightly further away. So let's see, what is R plus going to be here? So if we look carefully, R plus is going to be the distance from the center, you see that R, minus half the distance between the positive charge and the center there. So R plus is slightly less than R because the positive charge is slightly closer. R minus is going to be slightly further away, right? So it'll actually be R plus D over 2. So we need those two things because I want to calculate the electric field due to the whole thing. So I'm going to remove that little plus. The electric field due to the whole thing is going to be the electric field due to the positive charge plus, or minus because it's going in the opposite direction, the electric field due to the negative charge. So the electric field due to the positive charge is going to be K times Q over R plus squared. And then from that, I'm going to subtract the electric field due to the negative charge, right? So here I'm just taking the magnitude of the negative charge. So basically, the electric field due to the positive charge is this way. It's pointing up, so I'm making it positive. The electric field due to the negative charge is downwards, so I'm making it negative. Shut up, Ramus. The dog won't shut up. So it's the difference between those two charges is going to give us our electric field. So let me plug in for R plus and R minus, right? This becomes K Q over, so if I plug in for R plus, it's R minus D over 2 squared minus KQ, and then I'm going to plug in for R minus, so R plus D over 2 squared. And, you know, this is a pretty complicated problem. I can factor out the KQ, and I can factor out an R squared from those two denominators. And what I end up with is 1 over 1 minus D over 2R. So I factored out 1 over R from that, minus 1 over 1 plus D over 2R. And here, it gets complicated here. Let's just say you can do you can collect those two denominators, right? Find a common denominator, then simplify. So we're going to skip all those not fun steps, but stuff happens, right? It's a long derivation, and you get to this. You get to Q times D over 2 pi epsilon naught R cubed times 1 over 1 minus D over 2R squared squared. And so this is a pretty complicated term, but we're just going to look at the case where D over 2R is really small. In other words, when either the two charges are really close to each other, or or we're really far away from the dipole. And so we get a good approximate value for the electric field due to a dipole along that axis. And it ends up being QD over 2 pi epsilon naught r cubed. So we have now an expression for the electric field at a point here, right here, right here, due to this dipole. And this is the approximate value. And it is a good value. It works really well for estimating the electric field due to an electric dipole. Here's another calculation. So we just did this calculation here, where we calculated the electric field created by dipole. And we're going to label this thing P, Q times D. So the charge on each side, plus Q minus Q, times the distance between the two charges. We're going to label that P. We're going to call that the dipole moment. And that lets us rewrite our result, and you can see why the dipole moment is helpful. We're going to call that our dipole moment, and lets us rewrite the electric field as 1 over 2 pi epsilon naught P over Z cubed. Whereas if we were to do it along this axis, it's a little bit more complicated, but you can do this calculation, and you get a very similar one, except it's 1/2 the strength. And you get 1 over 4 pi epsilon naught P over Z cubed. So these are electric fields. You know, we're only able to calculate it approximately for some ideal situations along the axis parallel or perpendicular to it. And like I said, it's an important one. You know, the famous Mickey Mouse molecule, water, has 2 hydrogen and an oxygen, and it has an effective dipole moment, P. And we make that dipole moment, I'll talk about the direction that the dipole moment points in, but it has an effective dipole moment, P, of about 6.2 times 10 to the minus 30 Coulomb meters. And so if you put an electric dipole in an electric field, it's going to feel some forces, and it's going to start to move, right? So if I look at this dipole, this positive charge here is going to feel a force in the direction of the electric field. And this negative charge here is going to feel a force in the negative direction. So they're going to feel equal and opposite forces. So the net force is 0, but you can see that it's feeling something that's going to spin it around. So there's going to be a torque that spins this electric dipole around in an electric field. You can do a whole derivation. I'm not going to get into it, but you can calculate the torque as the distance of the force to the center of the pivot point. You can show that the torque on both the positive and the negative are the same. You can show that you can add the total torque together and then calculate the dipole moment P. Rewrite the dipole as QD as P, and then you can show that the torque, the magnitude of the torque on an electric dipole inside an electric field is P times E times the sine of the angle between them. And depending on how you define the vector P, you can rewrite the torque as P cross the electric field. We're going to do some cross products a little bit later on, but that's P cross the electric field. So here's P. The definition of P is that it's a vector that points from the negative to the positive side of the electric dipole. So P is defined as pointing from the negative side to the positive side, and its magnitude, remember, is Q times D. And the torque, the amount of, how much spinning force there is on this dipole, is defined as P cross E. So why is that helpful? Well, if I have a dipole like this, I'm just going to write like a little dumbbell. The dipole points from the negative to the positive, and what direction is this dipole going to get spun in this electric field? Is it going to get spun clockwise or counterclockwise? Well, if you look at it, right, this is going to feel a force that way, and that is going to feel a force that way. Remember, the electric field always exerts a force on the charge in the direction of the electric field if it's a positive charge. So this one feels a force that way, that one feels a force in the opposite direction. So this is going to feel a torque that is going to be clockwise or clockwise torque. Whereas if I were to draw a slightly different one, let's say I were to draw this one here, is this one going to be clockwise or counterclockwise? So if you think about it, this one's feeling a force that way, that one's feeling a force that way. So this force is going to be counterclockwise. Another example would be this crazy example here. If it's exactly pointing in this direction here. Oh, I forgot to draw the dipole moment. Here, if you look at this one, the force is that way, and this one, the force is that way. So the forces cancel out. They don't need any spinning. So this one here feels no torque, right? There's no torque in the cases where it's pointing uphill or downhill. So in this case here, the dipole is pointing that way, and the forces are going to cancel each other out. So there's going to be one force that way, one force that way. So the torque is 0 for this one as well. So a dipole in a uniform electric field will get spun one direction or the other, depending on its alignment. And you'll notice that this case here, the dipole is getting spun such that it tries to line up the dipole moment with the electric field. So this thing is getting spun clockwise to try to line it up with the electric field. And this one here, it's also going to get spun. So this dipole moment will get spun to try to point the arrow of the dipole moment in the same direction of the electric field. This one's already pointing in the direction of the electric field, so it doesn't move. This is a special case, right? It's pointing exactly against the electric field, but the forces just cancel each other out. If you were to spin this just slightly, it would whip around to the other direction. So this is sort of a basic calculation of forces on dipoles inside electric fields. You can do a similar calculation for the potential energy of a dipole electric field. And so the potential energy of a dipole electric field is minus P dot E, and it depends on the magnitude of the dipole moment, the magnitude of the electric field, and the angle between the dipole and the electric field. The lowest potential energy, so the lowest U is when P, the lowest U is when P and E are parallel. And so that means theta equals 0. Therefore, the potential energy is equal to minus P times E times cosine of 0, which is 1. So it's going to be negative PE. So that's the lowest possible potential energy situation. So I think that's enough of that. So here's an example. I'll let you play with this on your own, but this shows 4 orientation as an electric dipole inside external electric field, and I will let you enjoy this on your own time, but you can calculate the potential energy for different angles. Remember, the dipole moment always points from the negative to the positive. So for each of these, you got to remember to point the dipole from the negative to the positive and compare that angle it makes with the electric field. Okay, so just to give a quick example, let's say this electric field here is 100 newtons per Coulomb, and I have a dipole moment here that is I don't know what the magnitude, I don't know what the direction is exact. Well, I'm just going to write the magnitude. So the dipole moment has an amplitude of, let's say, 5.00 times 10 to the minus 20. All right, and that has units of Coulomb meters. And let's say that this angle here is 30 degrees. So I can calculate the magnitude of the torque. The magnitude of the torque is going to be P times E times the sine of the angle between them. And the potential energy is going to be P minus P times E times the cosine of the angle between them. And so you just need that theta is equal to 30 degrees. The electric field is 100 newtons per Coulomb, and P is equal to 5 times 10 to the minus 20 Coulomb meters. And so you can figure all that out from there. I just wanted to set it up for now. Here's another practice problem. You can, if you have a dipole where the charge on the dipole is plus or is 2e, and they're separated by a distance of 0.25 nanometers. So if you know the charge, it's 2e, and the distance, you can find p, because remember, p is just equal to qd. It says it's inside a uniform electric field of 3.4 times 10 to the 6 newtons per Coulomb. Calculate the torque and the potential energy when the dipole moment is parallel. So when it's parallel, that means when theta is 0. When it's perpendicular, that means when theta is 90 degrees. And when it's anti-parallel, that means when theta is equal to minus 180 degrees. Okay. Here's another example that I'll leave for you to try, and we can do this during the review sessions. A couple more practice problems. Oh, that's it.